This video is brought to you by mywayteaching.com.
Now let us consider the second case, that is observer is moving but the source is stationary. See, in order to derive the Doppler shift when observer is moving with velocity v0 towards the source and the source is at rest, so velocity v0 towards the source and the source is at rest, then we have to proceed in a different manner. So we have to work with the reference frame of the moving observer. In this reference frame, the source and the medium are approaching at speed v0 and the speed with which the wave approaches is v0 plus v. So we find that the time interval between the arrival of the first and n+1 crust is given by Tn+1 minus T1 n T0 minus n V0 T0 V0 plus V. The observer thus measures the period of the wave to be T0 1 minus P0 by V0 plus V. And we can write V is equal to 1 plus V0 by V. If V0 by V is small, the Doppler shift is almost same whether it is observer or the source moving. If you consider the third case, that is both source and observer moving. See, let us take the direction from the observer to the source as the positive direction. Okay, let us take the direction from the observer to the source in the positive direction and let the source and the observer be moving with velocities vs, see this is, and v0 respectively. Suppose at time t is equal to 0, the observer is at O1 and the source is at S1. O1 being to the left of S1, the sound emits a wave of velocity v, of frequency v and period t0, all measured by an observer at rest with respect to medium. Let us consider L as the distance between O1 and S1. Okay, at t is equal to 0 when source emits the first crust. So since observer is moving, the velocity of the wave relative to the observer, we can write it as v plus with v0, isn't it? The first crust reaches the observer at the time t1 is equal to L by v plus v0, and at the time t is equal to t0, both observer and source have moved to their new positions O2 and S2. The new distance between the observer and the source would be L plus Vs minus V0. This is the new distance. At S2, the source emits the second crust. Okay. This reaches the observer at a time t2. So we can write time t2 as at a time nt naught, the source emits its n plus 1 crust, and this reaches the observer at a time t n plus 1. So here in an interval tn plus 1 minus t1, we get the observer counts n crust and the observer records the period of the wave as equal to t, that is equal to t naught 1 plus Vs minus V naught by V plus V naught. The frequency V observed by the observer is given by so you just consider an example in your mind. A passenger sitting in a train moving on a straight track. Suppose she hears a whistle sounded by the driver of the train. What frequency will she measure? Here both observer as well as source are moving with same velocity. So there will be no shift in frequency and the passenger will not the natural frequency. But an observer outside who is stationary with respect to the track, there that observer is stationary but here the object is moving. He will note a higher frequency if the train is approaching him and a lower frequency when it recedes from him, isn't it? So we have defined the direction from the observer to the source as the positive direction. If the observer is moving towards the source, V naught has a positive value, whereas if observer is moving away from S, then V naught has a negative value, isn't it? On the other hand, if the source is moving away from the observer, in that case, that source frequency has a positive value, whereas if it is moving towards observer, isn't it? Then it has a positive value when it is moving away from the observer and it has a negative value when it is moving towards the observer. So the relative velocity of sound with respect to the observer is V plus V naught. In all the cases, it is same. Now let us see application of Doppler effect in short. See, the change in frequency is caused by a moving object due to the Doppler effect, and it is used to measure their velocities in diverse areas such as military medical science, astrophysics, and even it is used by police to check overspeeding of vehicles. A sound wave or an electromagnetic wave of known frequency is sent towards a moving object, and some part of the wave is reflected from that object and its frequency is detected by the monitoring station. This change in frequency we call it as Doppler shift, and even it is used in airports to guide aircraft and in the military to detect enemy aircraft. Astrophysics use it to measure velocities of stars, and even doctors use it to study heartbeats and blood flow in different parts of the body. Here they use ultrasonic waves, and in common practice it is called sonography. Ultrasonic waves enter the body of the person. Some of them are reflected back and give information about motion of blood and pulsation of the heart waves, as well as pulsation of the heart of the fetus. In case of the heart, the picture generated we call it as echocardiogram. Okay, we call it as echocardiogram. Now let us see one more simple problem. A rocket is moving at a speed of 200 meter per second towards a stationary target. While moving, it emits a wave of frequency 1000 Hz. Some of the sound reaching the target gets reflected back to the rocket as an echo. Calculate the frequency of the sound as detected by the target and the frequency of the echo as detected by the rocket. Okay. See, in the first case, the observer is at rest and the source is moving with a speed of 200 meter per second. Isn't it? Since this is comparable with the velocity of sound, 330 meter per second, the source is approaching a stationary target. V0 is equal to 0 and Vs must be replaced by minus Vs. So we must use the equation V is equal to V0 1 minus Vs by V inverse. So we get 2540 Hertz. Okay. Coming to the second part of the question, here they have asked the frequency of the echo as detected by the rocket. So here now the target is now the source because it is the source of echo, and the rocket's detector is now the observer, isn't it? Because it detects echo. So we can write Vs is equal to 0 and V0 has a positive value. The frequency of the sound emitted by the source. Here the source is nothing but the target, that is given by V. And the frequency intercepted by the target and not V0. Therefore, the frequency as of the echo as detected by the rocket is given by V in V plus V naught by V. That is given by 2540 200 meter per second 330 meter per second by 330. That is equal to 4080 hertz. So we got both the answers.